right, so we have a function here. It says find the following and justify answers. So we have intervals of increase, decrease, points of relative extrema. So what are we going to use to help us answer these questions? That's fine. Grab a warm-up packet. Oh, and we have new seats. Anyone remember where Porter sits? Okay. You're right over here. What are we going to use to answer these three questions? Do we remember from last week? The first derivative. Okay, so first, let's find y prime. Y prime equals, all right, my derivative is 1/2 minus cosine theta. All right, then from here we find our critical values. Critical values are where the derivative is what? 0 or undefined. I can't get an undefined slope out of this, so we're just going to set it equal to 0. How might I solve this? Add cosine theta to the other side. So 1/2 equals cosine theta. Now how do we solve this?
Unit circle.
Yeah, unit circle. Where is the cosine equal to 1/2? And we're doing the interval from 0 to 2 pi. What's the angle where the cosine is equal to 1/2?
Pi over 3.
Pi over 3 and?
Pi over 3.
Yes. All right, from here, we're gonna make a sine line. We're gonna put our critical values on the sine line, so pi over 3, 5 pi over 3. Normally I put negative infinity and infinity on here, but our interval is from 0 to 2 pi, so I'm gonna put 0 and 2 pi on here also. I like to do that anytime there's an interval so that we don't start doing extra stuff that we don't need to do. All right, intervals of increase and decrease. We need to test each one of these intervals to see if we get a positive or negative number. And I'm plugging into what? The derivative. To create the sine line, we're going to plug into the derivative. So why don't we just plug in 0? If we plug in 0 to this, 1/2 minus cosine of 0, is that negative or positive? Negative. All right, something in between pi over 3 and 5 pi over 3. How about pi over 2? 1/2 minus cosine of pi over 2. Positive. And the 2 pi, that's the same as 0, right? So that would be negative. All right, so now we have increase. Where's my interval of increase? Yep. Do you remember our justifications? It says justify answer. So I'm going to write because. Yes, except they called it y prime. So y prime greater than 0. All right, we are decreasing from 0 to pi over 3 union 5 pi over 3 to 2 pi because y prime is less than 0. Notice I'm using parentheses for everything, even though it was brackets in my interval. Just as a rule of thumb, anytime you're giving intervals of anything, just use parentheses every single time. The reason is that we don't say that something's increasing or decreasing at a singular point. It's always over an interval. So, yeah, and it's neither increasing nor decreasing at those values anyways. All right, points of relative extrema. All right, do we have a relative min? Where is it? Pi over 3 because we went from decreasing to increasing. So pi over 3, I want to get a y value. What am I going to plug this into to get the y value? This is when we're going to use the original. Anytime you're finding a point on the graph, you are plugging into the original function. To create the sine line, we use the derivative. Okay, so if I plug in pi over 3 up here, let's see, 1/2 times pi over 3 is pi over 6 minus, what's the sine of pi over 3? What? Yep, root 3 over 2. Do we remember our justification for a relative min?
Because y prime goes from
we have a relative max? Let's see, look at our sign line. Are we gonna go from positive to negative anywhere? Yep, 5 pi/3. And again, I'm finding a point on the graph, so I'm gonna plug that into the original function. So let's see, plugging in 5 pi/3 would be 5 pi/6 minus sine of 5 pi/3 is negative √3/2, so plus √3/2. Because y prime goes from positive to negative. All right, that's what we did last week. We have a multiple choice question to answer real quick. All right, they gave us the derivative. It says f prime of x equals, and it's already nicely factored. So we can easily find our critical values. Let's make a sign line. What are the critical values? 2, 3, 4. All right, we could pick a number smaller than 2, plug it in, and see if we get positive or negative. I want to show you another way you could do this. What's the overall exponent of our derivative? Yeah, I've got 1 here, 2 here, 3 here. Add that all up, you get x to the 6th. It has a positive leading coefficient, right? I don't see a negative out front anywhere. So what does a positive leading coefficient with an even degrees end behavior look like? It looks like this, right? Look, I've got all these written up here actually. Notice the evens go like this. If there was a negative out front, it would be like this. So if I know it's going to positive infinity on either side, I know this is positive and this is positive. Then I can still use my little cross bounce multiplicities to figure out what's happening at each x value. So at x equals 2, is it going to switch to negative or stay positive? Switch, because it's x minus 2 to the first power. That's going to change signs. That's a cross. What about at x equals 3? Stay the same because it's squared, so that's going to bounce. And let's just double check and make sure the last one makes sense. At x equals 4, 3 would be a cross, so that's going to switch to positive. So don't forget about your end behavior. That can fill in some of the blanks for you. All right, so do we have a relative max at x equals 2? Yes. Do we have a relative max at x equals 3? No. Do we have a relative max at x equals 4? No, we have a minimum there, so it's A. All right, today we're going to talk about concavity and the second derivative. Do we remember what concave up looks like? This. Concave up, concave down is this. A parabola is a perfect example of something that's either only concave up or only concave down. Last year in pre-calc, you guys visually looked at a graph and determined where it was concave up or concave down. You might have been given a list of points to choose from. Where do you think it's changing concavity? Now we're going to actually algebraically solve for those values. If the second derivative is greater than 0, the function is concave up. If the second derivative is less than 0, the function is concave down. Does anyone remember what that point is called when it changes concavity? Point of inflection. Very good. I'm going to draw this little y equals x cubed here to show you guys also. So y equals x cubed is a great example of, it's increasing the whole time. We know something is happening there at x equals 0. It changes from concave down to concave up. So you guys are going to be given a function and you've got to find where that point is and give the intervals. All right, if f of x is concave up, the tangent lines are blank the curve. Let's think about it. concave up looks like this. Where would the tangent line be? Below it. Anywhere I draw a tangent line is below the curve. If f of x is concave down, all the tangent lines are above the curve. Is anyone gonna go to the spooky story time tonight? I won't be here. I'm bringing the boys. They're gonna be Mario and Luigi. They won't wear the hats though, so. All right. Point of inflection. Whoop, there we go. Occurs when f of x changes concavity, f double prime of x changes signs. This is what we're going to use as our justification for a point of inflection. It's where f double prime of x changes signs. F double prime of x is equal to 0 at the point of inflection. Same exact process as what we did for increasing, decreasing, and relative max min. Eventually, we're going to get to the point where I'm going to give you the function, and you're going to use the first and second derivative to get all the characteristics, and then you're going to sketch the graph. All right, so this problem here, this is for sure something you might see on the quiz on Friday. So here's our function. We're going to find increasing, decreasing, local extrema, and then we're also going to do concavity and point of inflection. We're going to do all the characteristics we know for this one problem. It is always beneficial for you to use what you already know about a function. Like, this is a cubic function. So before I even start answering all these questions, I'm like, okay, I know it should start out increasing. Maybe it'll go to decreasing. Sometimes cubic ones don't. Like, you know, regular x cubed doesn't ever change to decreasing. But I know it's got to start increasing and end increasing. Start to picture these things. All right, for increasing, decreasing, local extrema, I need the first derivative. So what is f prime of x? X squared minus 1. There's our first derivative. I'm going to find critical values. That's where the first derivative is equal to 0 or undefined. So what are my critical values? Yes. All right, so my sign line, I'm going to have -1 and 1. Negative infinity, positive infinity. All right, again, you can just go back to what you know and you can start plugging in points into your first derivative to get these signs. But if I'm thinking about a parabola, x squared minus 1, I could probably already guess what these signs are going to be. What's it going to be over here? Positive, negative, positive. As we're starting high, ending high, it's going to cross in the middle there. All right, so where are we increasing? Negative infinity to -1 and 1 to infinity. What's my justification for increasing? I called it f of x, so we're gonna say f prime of x is greater than 0. Decreasing, negative 1 to 1, because f prime of x is less than 0. Alright, that matches what I know to be true about cubics. It's going up, then it goes down, then it goes back up. Alright, find all local extrema. Do we have any relative mins or maxes? Yes. We have a relative max first at x equals negative 1. How do I get the y value? What am I going to plug into? Original. This is the part people get confused on because you keep plugging into different things and you're like, wait, what am I doing? If it's a point on the graph, you're always using f of x to find the y value. Alright, so what do I get when I plug in negative 1? Negative 1/3 plus 1, so 2/3. Because f prime of x goes from positive to negative. We also have a relative min. By the way, relative and local are the same thing. So if it says local min max, it's the same as relative. 1, comma, let's see what we get when we plug it in. Let's see, wait. 1 minus 1/3 minus 1. Negative 2/3, yes. Because f prime of x goes from negative to positive. Alright, all of that was from last week. Now we're going to determine intervals of concave up, concave down, points of inflection. What are we going to use to find that? Second derivative. Alright, f double prime of x equals, what is the second derivative? I gotta go back and see my first derivative. X squared minus 1, so 2x. And yes, we are gonna do the exact same process again. Now we're gonna find critical values for our second derivative, so that's where it would be 0 or undefined. So equals 0, what's my critical value for the second derivative? 0. Okay, so x equals 0. Let's make another sign line. This time for the second derivative. I'm going to put negative infinity and infinity on here. And when I'm creating this sign line, I'm using the second derivative. So if I plug in a negative number into my second derivative, what do I get? Negative. Positive would be positive. And think about it, y equals 2x. Isn't that going to go negative to positive? Okay, so where are we concave up? 0 to infinity. My justification, because f double prime of x is greater than 0. Concave down from negative infinity to 0, because f double prime of x is less than 0. Are there any points of inflection? Yeah, at x equals 0. So point of inflection, that is a point on the graph. So to get the y value, what do I plug this into? The original equation. So when I plug 0 in up there, I get 0. Because, anyone remember the justification for this? Changes signs. Yep, it has to change from negative to positive or positive negative. There we have it. That's everything so far. Okay? Just change it. Yeah, you don't have to say goes from negative to positive. You can say that, it wouldn't be wrong, but this is less writing. So we don't care what sign it changes to and from for point of inflection. All right, you guys have, there's only 4 problems in your homework tonight. And you have already been given the function, the derivative, and the second derivative. So now all you need to do is find the critical values for each, create your sign lines, and then answer all the questions.